Hey everybody, welcome to Math with Ace. We are focusing on statistics and the linear regression exploration that we've been doing. So we've talked about bivariate data and how strong their relationship might be, how we would describe the slope and the intercept, how we would make a scatter plot, but how do we get the slope and the intercept? Where does that come from? What is this linear regression equation? So focusing on the same data set that we've had, where we have the miles driven of a Ford F-150 and the price of that same Ford F-150, and then we've graphed it in a scatter plot. What I have here is a line of best fit. This is the linear regression line that best fits the data. And what it means to best fit the data is that the sum of squares of the residual or the errors is minimized. So it is the line that best fits and creates the smallest area of squares. Well, what squares? We don't see any squares here, right? So what you do is for each of the points, you're creating these lines of how far away each of the data points are from that predicted line. And so our technology is running every single possible scenario of where the line could be at a full 360 and wondering which one is making the line, the square, the smallest. So we take this line and then we make the same distance horizontally and make it into a square. So we're drawing these little bitty squares all over the place to represent how far away each point is from the line into a square, and then we calculate that area. And by we, I mean technology. There are ways that you can calculate the value for A and for B by hand, but we are letting technology do it because once you get into larger data sets, it becomes very cumbersome to do each of these calculations by hand. So what we do is we have each of these squares, and then we find the area of each side squared or side times side, and then we add that together. So the smallest sum of squares is the line that best fits the data. If I was to take some straight line in here, I would get a bigger square here, bigger square here, bigger square here. And so again, the calculation is making those squares it's minimizing. So if you're in calculus or taking calculus, you understand minimizing and under constraints. So once we do this and we've determined which line minimizes those squares, then what we need to do is determine what is the equation of this line. And so recall in our previous video, we've talked about y equals mx plus b. That's the one thing that people memorize about linear equations. What is m? What is b? And in statistics, we're actually using y equals a plus bx, where a is our intercept, where the line, where our graph linear equation crosses the y-intercept, and b is the slope of that line. So if we look at this regression equation that we see right here, there's a negative slope because as you go from left to right, your graph is dropping. So higher miles is associated with lower price. So when high is with low, that's a negative relationship. And the intercept, I actually do have 0 miles driven. So the intercept is going to be somewhere in this area around 35,000. A lot of times in our viewing window, we don't have 0 on the graph. And so we don't necessarily get to see the y-intercept. But what we need to do is figure out how much is this graph changing? What is the rate of change for every mile driven? What is the price dropping? And where are we starting? What is the price when we haven't driven any miles? So again, there are calculations that allow us to determine the value of the intercept and the y and the slope by hand, but we're going to let technology do it for us. And what we do is we go into that 2 quantitative variables and we input our explanatory and response like you've seen. So we're taking this data and we're plugging it into Statlet. And we begin our analysis, but then what we're doing is we're calculating the least squares regression line and we get an equation presented to us. And I showed you the equation earlier this week, but let's see, we have the predicted y, which is the price predicted. So I could also say price predicted is equal to 35,314.7 cents minus 0.13966. I'm going to give a little bit further in my slope. I'm also told my sample size. I'm told the R squared, which is the coefficient of determination. I'm given a table that outputs some information. I can also calculate the correlation, which I did earlier in a previous video, which is 0.6782 negative. What is the coefficient of determination? How does it relate to R? What is this prediction? Let me write the prediction with the units or variables. So these are my regression equations. It is the least squares regression equation. It's the line of best fit that allows me to predict what the price is going to be based on how many miles I drive. So we're going to enter our data to quantitative variables. We go ahead and begin the analysis, and then we calculate that least squares regression line. And we allow that regression line to be presented to us so we can interpret the intercept, we can interpret the slope, and then we can use it to make predictions. So if you notice this R value, which is our correlation coefficient, if I was to take negative 0.6782 and square it, I wonder what that would be. Let's see. 0.6782 negative squared, I get 0.45995524, which looks like that. So the R squared value, that coefficient of determination, so we have the correlation coefficient and then we have the coefficient of determination. They are related. The correlation coefficient is the square root of the coefficient of determination, and the coefficient of determination is the square of the correlation coefficient. Those two go together. Okay, so you've got coefficient in both of them, but R squared is the percent of variation that is explained by the linear relationship. The coefficient of determination is the amount of variation in the response variable that is explained by the linear relationship with the explanatory variable. What does that mean? Okay, so let's write that down really quickly. Coefficient of determination is the percent of variation in the response variable that can be explained by the linear relationship with the explanatory variable. So if you were asked to interpret R squared, you would put in the variable, the percentage here, and instead of response variable, you would actually say what that is. And instead of explanatory variable, you would say what that is. So in this example, the response variable was price, and the explanatory variable was miles driven. And we had a value of 0.46, which is 46%. So 46% of the variation in price can be explained by the linear relationship with miles driven. So what does that mean? So there is this relationship here. I'm going to erase my squares. But what it's saying is 46% of the reason that price is the way that it is explained by miles driven. So the price is determined 46% by miles driven. Why else would the price be the way that it is? That comes down to color. It comes down to maybe it's got 4 doors versus 2 doors. Maybe it's the models are different. Maybe you have an SE versus an LE versus like an Overtrail. Maybe the car was in an accident. So there's all these other things that cause variation. But 46% of the reason that the price is what it is because of the miles. 54 is because of the other stuff. Okay? So from there, we have this equation, we have our slope, we have our intercept, we have our r squared, we have all sorts of information that is presented to us by calculating this least squares regression line. So what you need to remember is that this is a prediction. It's not a guarantee. That does not mean that this is true across all F-150s. It's based on the data that we have. And we should be cautious to stay within data that is from 0 miles to a little over 140,000 miles. If you go outside that range, we don't know if the relationship stays the same. Maybe it's no longer linear. Think about babies. When babies are born, they grow at a pretty constant rate and then it levels off. So if you're going to use a prediction, if you're going to use a linear equation from when you're talking about children to make a prediction, let's say for adults, maybe height and weight, you would have somebody that's 40 feet tall. So that is extrapolation. You don't want to extrapolate, which is making predictions outside of the explanatory range. Okay. So stick around, and in our next video, we're going to talk about making predictions and calculating residuals and analyzing our graphs. Thanks for watching.